So now we have these quad panels, right? And we're one step towards a kind of rational set of panels, but we need to know a little bit more about them, right? There's still going to be cases where they're twisting or they're not planar. So we need to have a way to understand that a little bit more. Okay, so the next step is that we're going to start to evaluate the 4-point surface. But let's hang out here for a second and review these two objects here, which are about data trees, right? So coming out of the, and we haven't used data tree objects very much in this webinar. So let's take a second and talk about these. Coming out of the BREP components, right, we have 225 branches to our tree, each one with 4 items, right? So our 4 points. If I wanted to, I could use a pointless display from vector point and connect the vertices to P so that I could see that we have labels for 0, 1, 2, and 3. So every panel is produced, or every isotrim is producing 4 points as its vertices, again labeled 0, 1, 2, 3. Now I want to make a 4-point surface from 0, 1, 2, and 3. So I need to reorganize how my points are being stored in Grasshopper. So instead of 225 branches of 4, from the flip matrix I want to have 4 branches of 225. That means these are all the 0 points down here, all the 1 points here, all the 2 points here, and all the 3 points here on every isotrim surface. All right, so the explode tree then allows us to isolate each one of those paths as separate outputs to connect to our 4-point surface. All right, good question. All right, so just because we created a 4-point surface, again, it doesn't guarantee that our surfaces are planar, right? So let's take a look at how we might test them for planarity. All right, so we know that a triangle is always planar, right? No matter what we do, a triangle can always be located on a plane. We might also know that a plane can be defined by 3 points. So if these were all tessellated into triangles, we know that everything would work, right? Everything would be planar. We can make it out of whatever material we want. Now, just as a preview, if you wanted to do that, you could just disconnect D for the first one, and you could go from A to C to D to get the other side of the triangles, right? So this is a purely triangular set of panels, and we know that this could be made out of any material, right? You can cut this out of flat material pretty easily. Okay, but let's say that we don't necessarily want to do that. We want to make quads, but we want to see how planar we can get them, and visualize how planar they are. All right, so what we're going to do is we're going to use that knowledge that a triangle is always planar, and the subsequent knowledge that we can create a plane from any 3 points to first create a plane and then test the 4th point of our surface to the plane for an indication of how planar it is. Okay, so first thing we want to do is we need to create our plane, right? So under vector plane, here are all the ways that we can work with planes. And let's use the plane by 3 points object. All right, so this asks for the origin and 2 points in the x and y directions. So let's just use 0, 1, and 2 outputs here from our explode tree. And that will create a plane at every one of these locations. And remember, you can change the plane display radius under the display preview plane radius option. Maybe I'll make it size 1, right? So there's my plane at the corner of every quad. All right. The next step is we want to find out how far away that fourth point is away from this plane. All right, so if we're back under the Vector Plane tab, there's another object here that we can use to find that distance, and that's plane closest point. Right, so this takes in a sample point and a projection plane, and it will give us not only the point that's on that plane as well as the distance for how far away it was. Right, so if we wanted to, we could take the fourth output here. That's our sample point. This is our plane for projection. And you'll see a new set of points. They're going to be either behind or in front of the fourth corner of each panel now. All right, so, and that will also tell us the distance. Okay, so if we knew that we always wanted to create quads, but we always wanted them to be planar, one thing we could do is we could say, let's replace the input of D here so that we make always a planar quad. And notice what we get here, right? This is kind of like a shingling effect where it opens up where there's a lot of curvature, and it will mostly approximate the original surface where there's less curvature, right? So here you can see on the underside too, we have it on this side because our surface is symmetrical. So these are always planar quads, and we just let the gaps here take up the difference between the original surface and the planar quads. Right? So if you wanted to, you could connect a surface from this edge to this edge, and you could close it up, and that would be one way. Or we can go back to thinking about this as having the capacity to bend, but only within a specific tolerance. So I'm going to go back to my original set of quads by connecting D up here. All right. So here, this tells me the distance that the fourth point is away from the original plane, thereby giving us a sense of the planarity of our surface. All right, so first things first, let's use some color feedback in our viewport. All right, so this is consistent with what we did just in the last file, and we're going to use our D values here. Let's go ahead and use them so that they're always positive, so we always have a positive distance. So to do that, I'll get you started, and then maybe you can tell me what to do next. If we go to Math, Operators, Absolute, this is going to be our absolute distance. All right, so we want color feedback based on this value. So right in the question window, there's going to be 3 steps, or I guess 4. 4 steps, 4 objects to finish off this file. So go ahead and type in the question window what your suggestion is for my next step. If I have the value that I want to color these things with, what do I do next? All right, you got it. First, we need to get the bounds of our numerical values. So I'll take the bounds from math domain, connect that up. Then I need to decompose my domain into its minimum and maximum. So that's domain components. Gives me my start and my end. Then I need to specify a gradient. And I'll use one of the other presets here. So L0 is going to come from the start, L1 from the end, and T from my absolute distance. And then I'm going to use my custom preview from Vector Color Custom Preview. All right. Now, because I used the absolute value, what is a small value here means that it's close to the original plane. So I think I want to swap my colors so that blue tells me, hey, that's good, that's planar. Yellow tells me, oh, that's okay. And red tells me, watch out, that's really curvy, right? That's out of plane by a significant value. And of course, if I change my original sliders that divide the surface up, you get different gradients applied to all of my quad panels. All right. And as an indication of how far we are on a plane, based on the size of my geometry here, my input profiles, and the units of my Rhino file, this tells me that I go from a completely flat plane, a completely flat quad, to one in which the gap between the planar version of it and the original is 0.15 units. Now that may be within tolerance, and that might be all you need. But if not, we're going to look at the next step, the next exercise, which will allow us to determine, based on this planarity, do we want to leave it as a quad or do we want to triangulate each side? All right, so are there any questions about analyzing, creating quads or analyzing them for planarity before we move further? Okay. So there was a question about the gradients and having the gradient correspond to some more specific numbers. So a couple of you correctly noted that this is always relative to the surface. So if I made a completely flat surface and then divided it up, I would still have some blue and some red panels. So one way to make this a little bit more specific would be to say, instead of just using the domain here, which comes from the distances that we have in this collection of quads, we could actually specify some values. So if we disconnect this, and we'll use a panel, and we'll say that 0 is always going to be, that's always flat, so that's good. We can keep it as a default 0 input. But we'll say that maybe our tolerance is 0.075 units, right? Like a little bit more than a 1/16 of an inch, right? So I'm going to hit OK, and that may be something that the manufacturer gave me for my facade system or something like that. So 0.057 is my tolerance. I'm going to plug that into L1. What that means is anything that's past 0.057 is going to become red. And then everything between 0 and 0.075 is going to be somewhere between blue and red. Right? So I could even increase the location of my yellow grip so that it very abruptly changes to red when I get close to that tolerance. And that would allow me to specify which one of these panels are too curvy based on a distance, not a relative curvature to the other panels. That's a really great question. Okay. All right, so that's a great lead into the next exercise. So I'll save this, and we'll maybe call this min tolerance, so that when you guys get this set of files, you'll have that as a note. Okay, so in the next exercise, what we're going to do is